Good morning, ladies and gentlemen. My name is Janusz Rajski, and today I'm very excited to talk about isometric test compression, or ITC in short. It is a new compression scheme that we presented at the International Test Conference in Seattle earlier this fall. Since there was a lot of interest in this topic and not everybody could attend ITC, we decided to record it. To keep up with the growing complexity of integrated circuits and the additional volume of new fault models, we have to constantly look for new and more effective methods that reduce the cost of test. In particular, methods that improve compression are of very high interest and demand. The purpose of this research was to develop a new compression scheme with higher compression ratio than the state-of-the-art solutions. At the same time, we wanted to achieve more flexibility in controlling power during shift. Both factors can reduce the total test time and therefore decrease the cost of tests. As you know, traditionally it was believed that low power during shift and high compression were mutually exclusive requirements. We wanted to challenge that opinion. In my presentation, I'll briefly review the state of the art. Then I'll present a new low-power decompressor with a template register. I'll introduce the concepts of templates and residual test cubes, which are fundamental to understanding of this method. Templates are derived from residual test cubes and communicate between the decompressor and ATPG to generate low toggle patterns that are easier to encode. We'll show experimental results and conclude. In the simplest possible classification, compression schemes can be divided into two major groups: single-step and two-phase techniques. Single-step methods communicate the constraints introduced by the decompressor directly to ATPG. For example, in Illinois scan, some scan cells permanently or temporarily assume the same values. ATP generates compressed patterns with those constraints. The decompressor in this case has relatively low encoding capacity, and ATPG has to compensate for that. There's no separate encoding phase. In two-phase methods, such as various receding techniques, ATP generates a test cube without any knowledge of the decompressor, and then we try to encode it by solving systems of linear equations. The decompressor typically has much higher encoding capacity, so the encoding works for arbitrary test cubes. The other major advantage of the sequential decompressor is that they can be reused as PRPGs in compression Elbis hybrids, which have recently become very popular in automotive applications. So the next logical step was to explore how a high encoding decompressor such as EDT could work with ATPG that has some knowledge of the decompressor and generates easy to encode patterns. This diagram shows an architecture of a low power decompressor. It has a ring generator that receives data from a tester and a template register that controls the cycles when the hold register captures values from the ring generator. The hold register drives scan chains of the design under test through a phase shifter. Notice that the ring generator receives data from the tester without any interruptions, even when the hold register is holding. This allows it to be charged and ready when an update occurs. There's no loss of data or bandwidth. This diagram shows scan chains filled in a manner consistent with the content of the template register. The positions of the register filled with 1s indicate the cycles for which the hold register is updated, T1, T2, T3, etc. Notice that between the successive toggle points, the scan cells in one scan chain have constant value, either blue or yellow. The decompressor has to encode only the first value in each specified segment. If there are any other values, they have to be the same, and they're easily sustained by the hold function. The content of the template register is typically amortized across 64 patterns, so introduces only minimal overhead. Here we have an example of a circuit where a single fault can be tested by a number of different test cubes. Some are easier to encode than others. The first one could be the result of a random fill in ATPG. The other three are less random. So which one is easier to encode, or which one is easier to remember? My favorite is the second one. We start with 1, then we immediately toggle it to 0. It is not only easier to remember, but also easier to encode. In addition, the stimuli consumes much less power during shift. A single scan shift operation toggles 14 flip-flops in the first vector and only 1 in the second. This method has a preprocessing step in which we identify the locations of the most likely toggle points. These templates guide ATPG to generate low-entropy test cubes. Test cubes are derived from the population of faults which we plan to target. The percentage of ones in the template register determines the toggle rate of the stimuli. We are shifting quasi-static patterns. The most fundamental observation leading to the discovery of test compression was that test cube had very low fill rate, single percentage points, in some cases, for many patterns, even below 1%. The other significant observation we made during the course of this research is that out of all the specified positions in a test cube, typically only less than 10% are essential. In this example, it is actually 8%. Essential means that every test cube for that fault must have these assignments. They are needed with 100% probability. The other positions are optional and interchangeable. In our experiments, we saw then more than half of the specified positions in test cubes got their values with probability 3% or less. This observation opens some new exciting possibilities for compression, because from a very large number of test cubes available for most faults, we can pick and choose the ones that are the easiest to encode. Let's now introduce residual test cubes. A test for the stuck at 0 fault on the output of the AND gate requires that both inputs have 1. We can say that any test cube for this fault requires each value 1 with 100% probability. For the 2-input OR gate, either input assigned to 1 could detect the fault, so one of the inputs should be 1 with 50% probability. Consequently, for the 3-input OR gate, any of the inputs with 1 can detect the fault, which translates to 33% probability. In a residual test cube, we only keep specified positions with probabilities bigger than certain threshold. A residual test cube for a fault is guaranteed to contain a test cube, but not every vector inside it is a test for that fault. That means that a residual test cube could be used to guide ATPG, but we cannot simply fill at random the don't care positions, which is the case with a standard test cube where every vector inside a test cube is a test for its fault. In order to compute residual test cube, a standard ATPG is combined with the computation of probabilities for the assigned values. As we inject the fault, get it excited, compute the values needed for propagation and justification, we also compute the corresponding signal probabilities. So finally, in order to obtain residual test cube from a regular test cube, we only keep the inputs with probabilities higher than certain threshold and discard the rest. In our experiments, a threshold of 5% produced good results over a wide range of designs. Residual test cubes are used to determine toggle points. Some have uniquely defined positions, and we call them prime toggling points. Some others span entire ranges. In the first case, there has to be a toggle point in one of the 4 places, in the second, one of the 2. The most effective templates are obtained by merging templates of many residual test cubes. The objective here is to maximize the number of residual templates covered by minimal number of toggle points. We start with the prime toggle points. These are the points between the adjacent scan cells with the opposite values. Therefore, they are necessary. They may also cover some other range. To efficiently cover all the remaining toggle ranges, we use heuristics derived from minimum cover problem. Here we are showing template generation for 4 residual test cubes. In reality, the process is iterative and the merging continues until the number of toggle points reaches a value defined by the target toggle rate. Finally, these operations lead to a template. A test template divides scan chains into segments with constant values. As you can see on this slide, the colors change only at the toggle points, so the residual test cubes are indeed consistent with the template in this example. Now, the actual ATPG process starts with the constraints introduced by the test template. Once ATPG assigns a value to a scan cell, the value is automatically copied to all other scan cells within the same segment. A fault that requires 2 different values in a single segment is untestable for that template, and it has to wait until a compatible template is generated. Templates are generated based on the so far untested faults, so eventually we will generate a compatible template for every fault. So far we have covered the various concepts and building blocks of this method. Now let's look at the overall isometric test compression flow. In this big loop, we always start with a list of undetected faults. We use a subset of them to generate residual test cubes and compute a test template. One template is typically used for 64 patterns. It is loaded to the decompressor and guides ATPG to generate and subsequently encode 64 patterns. The patterns are fault simulated and the loop is repeated until all faults have been covered. With a given test template, ATPG generates a test cube that is consistent with the definition of scan segment. That means that in one segment there can only be one polarity of logic value. There might be a couple of scan cells with that value specified, but all the cells in a segment might have exactly the same value and exactly the same corresponding Boolean equation. If in a segment there is at least one value specified, we move it to the beginning of its segment, and only these values need to be encoded using the input variables coming from the decompressor. Any additional values are sustained by the hold register and corresponding zeros in the template register. It turns out that on average 45 to 50% of the specified positions in test cubes are provided by the hold function. This is really good news because that means that this approach has the potential to improve the compression ratio by up to 2x. We implemented a prototype of this method and ran it on 9 cores configured with scan chains to channel ratio ranging between 15 and 400 and the decompressor sizes ranging from 16 to 64 bits. Using one template for 64 patterns and with 25% toggle rate, the new isometric compression significantly reduces the pattern count in comparison to standard EDT. Even though the amount of the reduction varies, we can see that every design benefits from it. On average, we see almost 44% reduction. With the template register, it is very easy to program a wide range of toggle rates. The number of ones in the template register determines the number of toggle points. The percentage of ones in the template register divided by 2 is the toggle rate for stimuli. This diagram shows some results of one of the designs. Here we can see that in terms of pattern count, the isometric compression run with 25, 17 and 12% toggle rate considerably outperforms the standard EDT run without any power constraints. They say that isometric exercise programs help reversing the effects of aging in the human body. The isometric test compression represents a new distinct category of compression technology, and it has great potential to rejuvenate test. It clearly outperforms the state-of-the-art techniques. In comparison to dynamic receding, which is one of the best compression methods, it offers almost 2x higher compression. Similarly to embedded deterministic tests, it is compatible with logic-based. In addition, it provides programmable toggle rate, which controls power during shift. Ladies and gentlemen, this concludes my talk. Thank you for your time. Please send me feedback. I really appreciate it. Thank you, and have a nice day.